All right, we're going to go ahead and process this a little bit. So if you're not quite finished, just fill it in as we go so that you can get it all completed and you have this sheet as something you can refer back to. All right. I guess I can just get rid of this. All right. So you were given this as the general form for what vertex form is supposed to look like. So we've got y equals this a value out in front. Then in parentheses, we've got an x minus h. That quantity gets squared, and then we have plus k on the outside of that. And so the first task was, based on what this general form looks like, in each of these cases, what would you identify as the h value and the k value, and write that in an ordered pair? Okay? All right, so, yeah, we'll stay with green. That's good. Katrina, what do you think on this first one? What do you think h is? -2, 0. Do you agree with that? Close, but not quite. Okay, how should we fix it? 2, 0. Why is it 2, 0 instead of -2, 0? Henry?
Because of the equation, there's a negative for the h.
Right. The minus is part of the general equation. So that can make h a little bit tricky sometimes because our brain wants to just go with what we see, and we see a -2 there, so we want to say h is -2. But in order to get the negative, the -2, h must have just been 2 because the minus was already part of the general form. Does that make sense? So our h here is actually just a +2, and then the 0 because there's nothing being added out here. Okay? All right. Amy, what do you think h is on our second one?
3.
Sorry?
3.
A 3? You agree with that? Because it's that same tricky bit, right? If it's x minus h, and I end up with x plus 3, what must have h been? -3. So our h's are always going to look like the opposite of what we really see there. And it's all because of that silly little minus that's part of the original form in the first place. So if I end up with an x plus 3, my h must have actually been negative so that the minus and the negative turn plus. Okay? How about a k value, Amy? -1. Good. Luckily, k is what it looks like. So that one's easy. All right, how about for our next one? Julian, what do you think h and k are?
-2, 4.
-2 and 4. Everybody agree with that? Okay. And for our last one, Aaron, what do you think? -3 and 1. Everybody okay with that? All right, so that's what that first column should look like. Okay, then we were supposed to write standard form. So each of these, we're going to multiply it out, we're going to simplify it, we're going to get it into standard form. So we've already talked about this first one. We said that we would end up with y being equal to x squared minus 4x plus 4. So I'll go ahead and fill that in. How about the next one? If we take x plus 3 squared and then subtract 1 from it, what will we get, Emma?
Y equals x squared plus 6x plus 8.
Okay, everyone agree with that? Look good? Okay. How about our next one? Y equals -3 times x plus 2 quantity squared plus 4. Sean, you got this one?
Y is equal to -3x squared minus 12x minus 8.
Oh, hang on a second. I got messed up. Y equals, okay, -3x squared. What did you say after that?
Minus 12x.
Minus 12x?
Minus
Minus 6?
6. 8.
8. Oh, my bad, my bad. Here we go. Magic eraser. Minus 8. Everybody okay with that? That look okay? All right. And then our last one, we've got y equals 2 times x plus 3 quantity squared plus 1. Andrew, what do you think?
Oh, we got y equals 2x squared plus 12x plus 18. Oh wait, sorry, plus 19.
Magic eraser. 19. Okay, everybody okay with that? Those all look good? All right, so what happened then when you go back to what we did with the last example? Using our standard form, you do your x equals negative b over 2a, then you substitute that in for x to get y. What do you get for a vertex? Jessica? 2, 0. What do we get for a vertex on this one? Chloe? You think it's going to be negative 3, negative 1? Are you sure? Are you confident?
Yes.
You want to ask anyone to confirm for you?
I'm okay.
You're okay with it? All right. How about for our third one? What did we end up with when we did standard form? Yeah, Henry?
Negative 2, 4.
Negative 2, 4. And on the last one, David, what do we get? Negative 3, 1. So the moral of the story is, what?
It's the same.
H comma k is a vertex.
Is this the same as the absolute inequalities that we graphed?
Very similar. Yep. Yep, exactly. Good connection. So remember what we were talking about when we did the review and we were trying to graph the two variable absolute values, and we talked about h and k and how h and k was going to be where the corner was. And then from there, your b would go up or down depending on what a was. Same idea exactly. This is what would be called the transformation form of the quadratic. But in quadratic, it generally gets called the vertex form because of the fact that you can directly tell what your vertex is just by looking at this equation. You can tell what your h is, you can tell what your k is, and h comma k is going to be your vertex. Okay, was there another hand up? I thought somebody else had a question. Okay, so when you get down there to the bottom then, where they ask you, use your observations from part 4 to find the vertex of each of the quadratics below. Do not write the equations in standard form. So for part A, if we have y equals x plus 4 squared minus 2, Sophie, what's our vertex for that going to be? Negative 4, negative 2. Okay, we don't have to go through this process of changing it to standard form first and then getting our vertex that way, because we can now see hk is just going to be our vertex. Does, I'll wait with that question. B, y equals negative 3 times x plus 3 squared plus 2. What's the vertex for that one going to be, Damien?
Minus 3, 2.
Minus 3, 2. Did the negative 3 out in front affect our vertex? No. It's got a different job. But it has nothing to do with our vertex. Okay? And for part C, y equals 2 times x plus 5 quantity squared plus 2. Julie, what would we get for a vertex?
Negative 5 and 2.
Negative 5, 2. Okay? So, what we're going to find is with all of these different forms, and there are 3 of them total, with these different forms, certain things are really easy with that form, and certain things are not quite so easy. With vertex form, the easy thing is the vertex. Okay? So if we actually try to graph a couple of these real quick, let's take a look at y equals x plus 3 quantity squared minus 1. What did we say the vertex of that was going to be? So negative 3, negative 1. Okay, negative 3, negative 1. That puts me right there. But even though it's a different form of the equation, the process for graphing is not any different. We still have to have 5 points. We still have to label our vertex. -3, -1. We still have to label axis of symmetry. Ooh, that got really bad there, didn't it? Try that again. Try to stay on my line a little better. Yeah. How should I label that line? Good. Whatever my x value is here, the equation x equals that. Whoops. Need to change back to solid here. X equals -3. That becomes our equation for our line that makes up the axis of symmetry. What about y-intercept on this one? Is it as easy to find as it was on the standard form?
Nope.
No, not quite that easy. But can you still find it? Yeah, you still have to work, you just have to work it out. So if I put 0 in for x, that's going to give me 3 squared, which is, and then subtract 1 and I get 8. So 1, 2, 3, 4, 5, 6, 7, 8, right there. Okay, so y-intercepts on standard form and on vertex form can be really helpful as long as they're relatively close to your vertex. Now, if my vertex was out here at like, -10 something, I probably am not going to want to try to find the y-intercept because it's probably going to be so large it's not going to fit on my graph anymore, and then it's useless. Okay, but as long as I'm within, I don't know, 2, 3, maybe 4 squares from where my vertex is, where my axis of symmetry is, then that can be a really helpful and pretty easy point to find. All right, what would be another good point to use then, based on what I have here? A what? A 1? So would I want to go farther out here?
No.
Maybe -1, something in between. Since I'm already 3 squares away to get to my y-intercept, I want probably something else on the right side, but probably something in between my vertex and my y-intercept. So if I try -1, -1 plus 3, 2, square it, -1, 3. So -1, 1, 2, 3, right there. All right, so I'm up to 3 points. How am I going to get my other 2? Reflect. So if I'm 2 to the right, I'm going to go 2 to the left for that one. And I'm 3 to the right there, so 3 to the left there for that one. And try to draw it as best I can on my smartboard. There we go. Okay, makes sense? How about on this one? What's my vertex going to be for y equals -3, x plus 2 squared plus 4? -2 what? 4. Okay. So ooh, this is going to get kind of crowded. -2, 1, 2, 3, 4. Right about there. Okay. Which way would we expect our parabola to open on this one? Down. So I'm going to label this kind of up above so it doesn't get in the way of where I'm going to draw things. And for my axis of symmetry, how am I going to label that? X equals what? -2. Good. Okay. What would the y-intercept on this one be?
4. No.
Don't think it's 4.
-8.
-8, because we have to work it all the way through, right? So the 0 here gives me 2 squared, which is 4, but then I have to multiply it by -3 and add 4 to it. I get -8. 1, 2, 3, 4, 5, 6, 7, 8, right about there.
Should we graph both graphs in the same?
You can, depends on what you have available to you. I'm giving you some graph paper that you can do things on if you want to do them separately. If you can tell them apart, especially if you do them differently on the same one, like one in pencil, one in pen, or if you've got colored pencils or colored pens, you do them in different colors, then you can put a couple on the same graph. All right, so I got 2 points. Where's a good place to find a third one? Maybe -1, because that'll be on the same side here with my y-intercept. So, -1 plus 2, square it, times -3, plus 4, -1, 1's a point. And then we'll reflect. Right there, right there. This is the skinny one. Which kind of makes sense because the A has the same kind of effect that it did on our absolute values. Remember, the bigger the A got, the skinnier our V got, because the slope of the right side would get steeper. It has a similar type of effect on parabolas. The bigger the A gets, the skinnier your parabola is going to get. Okay? Easy enough? Questions on the vertex form? All right. Form number 3, factored form. You have seen factored form a lot in the past, but it's not usually in graphing. It's usually when we're trying to solve things. We're trying to solve a quadratic equation. One of the things we try to do is factor it. But we can also use the factored form in graphing. Okay? Now, if we were solving this, we would have an equation something like this. Right? We would actually be setting this equal to 0, and then finding our solutions that would make our equation equal 0. And what would those solutions be? 3 and -1, because of our zero product property that says if I'm going to multiply 2 things together and get 0, one of those 2 things had to be 0. So the 3 would make the first factor a 0, the -1 would make the second factor a 0. But if we take this same thing and we think about what's going on graphically when I do this, on the graph, what kind of points do I have if the y is equal to 0? X-intercepts. So graphically, getting solutions like this translate into x-intercepts. So that means I have an x-intercept at +3, and I have an x-intercept at -1. Okay, how does that help?
There's 2 points.
Sorry?
Those are like 2 points that you use.
Okay, so I've got 2 points out of the 5. Awesome. What else can I figure out, Julie?
If you add those 2 numbers and divide by 2, then you should be able to get the axis of symmetry.
Good. So if I add these 2 together, what would that give me? A 2. Divide by 2. I get 1. If I draw a line here at 1, try to anyway. Wow, I'm really getting crooked here. See how my axis of symmetry is right in the middle of my 2 x-intercepts? Well, that shouldn't surprise us because we know that parabolas have this symmetry going on, that the one side reflects the other side. So if I have these 2 x-intercepts, they're reflections of each other on the parabola. And so my axis of symmetry had better be going right down the middle of those 2. And the way to find them is to simply take what we would say P plus Q and divide it by 2. So the general form of this looks like this. Come on. Hello? There we go. That's a cube. Oh, wow. Let's just try that all again. There we go. Okay, so whatever these numbers are, the p and the q, we add them up, we divide by 2. And again, notice the general form is written as subtraction. So if it's x minus 3, then the p-value is actually 3. If it's x plus 1, then the q-value is actually negative 1. That's what we're going to use. Okay, so in this case, not negative, that meant we ended up with x equal to 1 for our axis of symmetry. But it also then tells us what? It tells us the x value of the vertex, because the vertex has to be on the axis of symmetry. So now I can go back to my equation, substitute 1 in, and find out the y that should go with it to get the vertex. And what's that going to give us? A negative 4. And which way would we expect this to open? Up, because technically what's my a value right now? A positive 1. Okay? So it makes sense then that I end up with a 1, negative 4, because based on where that is in relationship to where my x-intercepts are, a parabola that opens up makes sense. Okay? Can I find a y-intercept on this one? Yeah, you can always find one. Just depends on how much work you have to do to get it. On the standard form, there's no work. You just look at it and go, oh, constant, there it is. On vertex and factored form, you have to actually kind of work things out. So if I put 0 in here and 0 in here, what am I going to get? Negative 3. So my y-intercept is going to be at negative 3 right there. Stop it. Okay, if it's going to be at negative 3, then that means my reflection would be put right about there. And boom, 5 points. There's my graph. So, factored form, it's really easy to find what? X-intercepts. The other two forms, it's not easy to find x-intercepts. And really from standard form, the only way you can find x-intercepts is if you factor it first. From vertex form, yeah, you might as well just give up. It's just not easy to find x-intercepts from vertex form. Okay? But in this case, it's kind of nice because if I already know the x-intercepts and then I can find the vertex, I've already got 3 of my points. I just need 2 more. And then I can draw my graph. Questions? All right. Just to double check this to see that it really does work, can you change this factored form into standard form?
Yes.
What would it be? I'm going to change color on this. Y equals what?
X squared minus 3x minus 3.
Okay, so the minus 3x and the plus 1x would give us negative 2x and then negative 3. Okay, go back and use our original method. What would the vertex be if that was the standard form that I gave you? X would be what? 1. How would we set it up to get the 1?
Negative 2 over negative 2. This is negative b over 2a. So
Negative b over 2a. So negative b would be
2.
a 2, because it's the opposite of what's here, and it's already negative 2. And then over 2 times a, which is 1. So we're going to get 1. Oh, I guess I never actually wrote the, uh-oh. I would have lost points on this. I didn't label my vertex. We're gonna go back and do that quick. Or do we end up 1, -4, yeah? Okay. So 1 for x, 1 for x, that seems promising. Now if we substitute 1 back in, 1 squared is 1, minus 2 times 1, which is 2, so that's a -1, minus 3, we'll get our -4. So we can confirm that this really does work by changing it back into standard form, but it's not necessary to change it back into standard form to figure things out. We should be able to figure out from the factored form we're given what our vertex is going to be and go from there. Okay? So these are the 3 different forms. We've got standard form, we've got vertex form, we've got factored form. In all 3 cases, the most important point to find is what? Vertex. It's the anchor. Okay? Everything else kind of comes from knowing where the vertex is. The everything else part kind of depends on which form you have. If you're looking at the standard form, then it probably is going to include your y-intercept because that's easy to find. With your other forms, probably y-intercept will also be found because it's not tough to find. Okay? If it's factored form, the everything else should include your x-intercepts. You should be able to tell those from that factored form. Okay? And then, if all else fails, just pick some x values close to your vertex and plug them in and get some points. So you must have the vertex as your first point, and you need 5 points total to make sure you've got a really good graph. Okay? And don't forget to label stuff. Your axis of symmetry and your vertex. Okay? All right. So, let's see how well we are understanding what we've been talking about. We're going to do a little game. And in this game, we're going to actually be able to get up and move a little bit, because we've been sitting for almost an hour. I forgot to make signs, so you're just going to have to remember this. Ready? Okay? I'm going to give you 5 multiple choice questions. Every question has an A, B, C, and D answer to it. And you're going to indicate your choice by the corner you go to. Okay? So that means that this corner up here is going to be corner A. Okay? So if you think A is the correct answer, you're going to go to this corner. Back there by the filing cabinets will be corner B. By the door over here is corner C. And by the door up here is corner D. So I'm going to show you a problem, give you a second to think about it, or maybe work something out if you need to, and then based on which of the 4 answers you think is correct, that's the corner you're going to go to. Make sense? Yeah? All right, everybody stand up. All right. There's no talking on this. You have to decide on your own. If you talk, you lose, you have to sit down. Okay? All right, here's your first question. So remember, it's A up here, B, C, D. All right, so we seem to have unanimous consensus that it should be B. It opens down. Amy, why did you choose B?
Because the A value is negative.
All right, so our A value is this 2, this -2, excuse me. And because it is negative, we should be opening down. Okay, pretty easy. All right, come to the middle. Next question. Again, A, B, C, D. All right, another unanimous decision. Katrina, why'd you say up?
It's positive, the A value.
Okay, so our A value here is this 0.5. It doesn't matter if it's integer, fraction, decimal, whatever. What matters is positive or negative. So as a positive 0.5, it's going to go up. All right, good. Y'all got that one. Back to the center. You might need some paper for this next one. I don't remember. The next three are more about vertices, so some you might have to work out, some you might just be able to tell. All right, ready? Here's the next one. You need some paper to work it out, that's fine. You can do it in your head, that's great too. Remember, it's A, B, C, D. Alright, so everyone seems to have picked a corner, but we're not unanimous this time. So, does the crowd win, or are these two brilliant? Okay. Sean, why did you think your answer?
I isolated the X.
Okay. Sophie, what do you think? Okay. All right. Well, let's ask these guys. See if they're feeling any better about it. Julian, what do you think?
I guess I just did it like you taught us, and then I got.
Be more specific.
I did like the negative b over 2a, and then I got the x, and then just plugged it in.
Okay. David? Same thing? You agree with that? Henry, does that sound good?
Yep.
Okay. And so C ends up being our answer because negative b is going to be negative 6 over 2a. 2 times 1, that's going to give us the negative 3. So that eliminates A and D as possibilities. So now to decide whether it's B or C, we have to substitute negative 3 back in. So that's going to be 9 minus 18 plus 13. So it's going to be the C value. Okay? So we do have to make sure that we have it straight in our head. Which type of equation is this? And then what do I look for to get the vertex in that type? Okay? So unfortunately, standard form, you can't just tell by looking at it. Okay, that's the vertex form. All right, standard form, you got to do some work. Okay? All right, back to the middle. 2 more. There's our next one. B. A's up here. B, C, D. All right, this one seems to be unanimous again. Harry, why'd you choose B?
Oh, because H, K is 2,
Okay, so which form is this?
vertex form.
Vertex form. So that means we can just look at H and K and get what our vertex is going to be. But the trick is, which it looks like you were all very brilliant and didn't fall for the trick, is not to read this as a negative 2, right? The minus is part of the form, so H is just 2, and 2, 5 is our correct answer. Excellent, nobody fell for the trick. All right, one more. Ready? Are you stuck or just working? Got it? Aaron, how about you? Are you stuck on something or? Okay, hang on, because we're going to let one of these explain it. All right? Anna, why did you choose D?
As first, I try to find 2 points. So if I want to make y 0, the x value will be -2 and -4. So, and then you add -2 and -4 and divide it by 2. And you then find the axis of symmetry, which is x equals -3.
Okay.
So now you have only A and B. And then you plug -3 into the equation, and you get -1 times 1, which is -1, and then times -2, and then you get 2. So it's D.
Okay. Did that make sense? What you said? What you have to be careful about, and I wasn't being quite tricky enough, because honestly I was putting this together about 10 o'clock last night. But what you have to be careful about here is to not take the +2 plus the +4 to divide by 2. It's got to be those opposites again. Because the general form is x minus p and x minus q, and it's p plus q divided by 2. So it's a -2 and a -4 that we're adding together, dividing by 2 to get the -3 for x. All right? And then when we substitute that in, we end up with the +2 for y. Okay? Does that make sense? All right, good. Have a seat. All right, so the last thing I want to talk about a little bit is there are a few questions in your homework where it not only asks you to graph your parabola, but then it asks you to compare the graph that you get to the graph of y equals x squared. Okay, so first I want to talk a little bit about what kind of language you should use for that answer, and then we'll go back and actually talk about a couple of the graphs we've done and talk about how it would compare. Okay? So the first thing that you could look for is whether your graph is in a different position from what your y equals x squared is. So if your vertex is somewhere other than 0, 0, then your graph is moved. And so we talk about that then about shifting. We say it's shifted to the left or the right, we say it's shifted up or down, and we say how much. So it's shifted to the right 3 units and up 2 units. It's shifted to the left 3 units and up 5 units. It's shifted to the right 1 unit and down 6 units, whatever. Okay? That's just like taking your parabola and sliding it around to a different spot. Okay? So that's one thing that you can look for to make a comparison. You can also talk about whether it got reflected or not. If your parabola normally opens up for a regular y equals x squared, but now you have a parabola that opens down, then that means that you ended up reflecting it through the x-axis. So that's another thing that you could state as a comparison. My graph, my new graph that I just drew, has been reflected through the x-axis compared to the y equals x squared graph. Okay? And then finally, the other one you can talk about, there's more specific language for this that we'll get to later. But for right now, just say whether your graph ended up narrower or wider than the normal y equals x squared. So did you end up with a graph that's narrower or skinnier than what it would usually look like? Or did you end up with a graph that's wider than what it normally would look like? And you can just use that language. Okay? So the three kinds of things you're going to look for. Did it shift, move around? Did it reflect? And did it get narrower or wider? Okay, we don't need to comment on anything other than that. So if we go back up here, maybe, go, let's take a look at a couple of these. So let's go back to our first one. Okay, first of all, what does y equals x squared look like? Where's my vertex? 0, 0. Okay, what are some other good points? 1, 1, 1, 2, 4. I count it off here, right? Okay, and then if I reflect those, because again, we really only need 5 points. So normally, y equals x squared looks like this. Okay, so now how would you say the orange graph, the graph of y equals 2x squared minus 8x plus 5, compares? What would be one thing we could say? Claire? Oh no, sorry. Cheryl. Sorry. Cheryl, what do you think? What's one comparison you could make? Okay, so we moved over 2 to the right. Okay, Julian, what's another?
It went 3 units down.
And it went 3 units down. So we moved it to a different location. And that move generally corresponds with your vertex. So a positive x value means you went to the right, a negative x value means you went to the left. A positive y value means you went up, a negative y value means you went down. So if you know what your vertex is, you can talk about how it got shifted. Okay? Any other comparison that we can make? Yeah, so our orange graph is narrower than the black graph. Okay? And that again is because of our a value. Having an a of 2 made things happen more quickly. Instead of going 1 to the right and up 1, now I go 1 to the right and I go up 2. So things are changing twice as fast on my orange graph as they did on my black graph. And that's going to give me a narrower graph compared to the y equals x squared graph. Okay? So if this was when we were meant to compare, our answer would be our graph shifted 2 to the right, it shifted 3 down, and it is a narrower graph than y equals x squared. That would be your answer. Make sense? Okay, let's try one more. How about this one? How would that one compare? Okay, so shifted 1 to the right, shifted down 4. Anything else? Is it? No, it's still 1 over, 1 up, 2 over, 4 up. Okay, and why is that? Because what's my a value this time? 1. So that means whatever the normal scale of the graph is, I'm multiplying it by 1, meaning I'm keeping it the same. So there's no wider or narrower on this one. Is there any reflection? No, it's still opening up just like y equals x squared normally does. Okay? That one was pretty easy. Let's take a look at this one. How about that purple one? How would you compare the purple one to y equals x squared?
The direction of the opening is different.
Say again?
The direction of the opening is different.
Okay, so what does that mean in terms of that language we talked about?
Reflected.
So we've got a reflection through the x-axis. Please make sure that you state through the x-axis. We're not going to talk about it right now, but it is possible to reflect things through the y-axis, so we need to be specific. So reflection through the x-axis. What else? Anna?
Like it moves to the left.
All right, so we shifted 2 to the left and 4 up. Anything else? Any other comparison? And our graph is narrower, because with that 3, negative means it's going down, the 3 means it's changing fast. So it's going to become a narrower graph than the normal y equals x squared. So that one's got everything going on. Reflection through the x-axis, shifted 2 to the left, 4 up, and is narrower than y equals x squared. Okay, make sense? All right, so our final thing then here is we're going to do a little exit slip activity. You can work on it together at your tables of 3, but each of you needs to fill out your own answer sheet. Okay? And so what I'm going to give each set of tables is an envelope. Inside of the envelope, there are 10 graphs and 10 quadratic functions. Okay? And they're mixed up. Some are standard form, some are vertex form, some are factored form. Okay? Your job is to match the correct equation with the correct graph. Okay? The graphs have little letters up in the upper left-hand corner, and those are the letters that are listed on your paper. So once you decide this is the equation that goes with this graph, and this is graph D, then right beside D, you're going to write out the equation that you decided goes with that. Make sense? Okay? So you can work together to do the sorting and matching, but you each need your own slip. When you hand me this slip, I will hand you your Chapter 1-3 post-test, so you can take a look at it. If you have questions, you can hopefully maybe ask today, or if not, don't have time today, email me and we'll set up a time that you can ask questions about it. When you are finished with the questions, you're going to put it in your folder back there in the blue table. The gray set of folders is for our class. And each of you has a folder with your name on it. And that's where all tests must go. Tests cannot leave this room. So once you're done looking at it, then you put your test in your folder back there in the back. Okay? All right.
How it goes. This one goes down. Okay. So I think it's this one. I think it's missing a graph. I'm missing a graph. I'm missing one graph. I'm not even checking. Because there's a problem. It's look. Oh, I found it. You messed up. Julian, I found it. Wait. Neither this one. Is there another one? This is minus 3 is Dude, this minus 3 is so this one goes with this one. Okay, what was the other one? This, where's the other minus one? Oh, here we go. This one goes with this one. This one's 5. Yeah. So E is...
When you bring up your actual exit slip, if everyone's done in your group, also bring the envelope up with you.
Yeah, I got it. Is this one? This one? So it should be 1 and 5. No, it's not. So 6. I think the 5 is 1, 2, 3.